So I have a very generic title, maybe the most generic of the conference, after Ben, perhaps, but we're up there. But I'm just going to talk about directions that I think are promising at the intersection of machine learning and cosmology. First, let me give you some context. We had a lot of context over yesterday and today, but I want to give you a bit of my perspective on cosmology and machine learning. And yeah, we're all super excited about all the different data sets we're getting in the next 5 years, all across different wavelengths, etc. We call this like big data cosmology, right? We're all very excited. But actually, I think if we were to be honest, we should call this the era of big one-dimensional data cosmology, right? So even in this conference, a lot of what we've seen is working with one-dimensional summaries of our favorite data sets, right? But in particular, yeah, for galaxy clustering, that I'll talk more about today. Normally, we look at the two-point correlation function or even just the BO. These are like the latest DESI results, right? So this is the state of the art in galaxy clustering data analysis, right? And also what we're doing is 5-dimensional cosmology, right? So usually we're trying to infer like 5 cosmological parameters. But we've seen a few examples today. So Ben, for instance, was talking about initial condition reconstruction or like high dimensional inference problems that will be very interesting to solve over the next few years in cosmology. And I argue that for that, we actually need machine learning. Like, it'd be very, very painful to do things otherwise. And in particular, we need to care about astrophysics, right? So I think the people that are here understand this very well, right? Astrophysics is not just the nuisance parameters in our analysis, but it's actually interesting physics that we want to constrain. Hope we all are in the same page, at least in this room. Right? Now, there's a lot of interesting things that we can do with machine learning, and these are some like proof of concept applications that I've worked on. But yeah, there's loads of examples throughout the week we've been seeing. And in particular, if you look at applications of simulation-based inference, astrophysics has a big role there. So this is a compilation made by colleagues, Jozef Sharma, on GitHub on papers and simulation-based inference. You could argue that he's biased because he is himself an astrophysicist, but actually it is a pretty thorough compilation. So if you look at the papers there, this is a section on astrophysics. There's more and more and more. There's a lot on astrophysics. I think at some point we get a few in particle physics and some neuroscience, but a lot of astrophysics. Now, when you go to the application to real data section, this is a tiny section. So the first thing, why do we need an application to real data? We should all be trying to do inference in the real universe, right? To learn something interesting about the universe we live in and not some simulated universe. Yeah, that would be great. Not the case. Well, we've seen some examples, right, of how hard it is to actually make the leap. This list should now be a bit longer than it is here, but still, it is pretty, pretty short. And actually, the examples we've seen maybe weren't as impressive as we would have hoped, right? Because we had to be very conservative in the kind of analysis that we have to do. So this is the factor of 2 that Bhuvnesh was talking about the other day, right? So we were hoping to get much better than a factor of 2, right? So what's happening here? Well, it is hard to model real data, right? And I just wanted to highlight work by 2 students at Harvard. So Izan gave a talk a few hours ago. So if you missed it, please have a look at the slides. And Elena Britton will have a poster this afternoon on halo mass estimation. But they've been both looking at model misspecification and how can we overcome this. But I wanted to also start with something similar to what Ben showed this morning, right? The cost of cosmological simulations to really get an idea of the scale of the problem we have in hand. And this is an example from the simulations used for DESI analysis. So this is the Abacus Summit suite. So it's pretty high resolution because we want to get to low mass galaxies. And we have about 100 of these simulations. So in total, we have about 60 trillion dark matter particles, and that took about 15 million CPU hours. So pretty costly, but this is nothing compared to a high-resolution hydrosim, right? So TNG50 took about 100 million CPU hours. So scaling this up in terms of CPU compute sounds horrible, right? In particular, if we put it together with the machine learning requirements, so this is an example I'll show you later, but if you look at the solid line, it's showing the convergence of the machine learning algorithm as a function of the number of training simulations. So it converges about 10 to the 4. You could argue for a 10 to the 5 case, right? So we really need loads and loads of simulations. And yeah, again, Ben and Matt had some really great examples as well on how this scaling is going to kill us, right? We try to go this way. So today, I want to talk about, first of all, whether we can use inductive biases to make this scaling maybe a little less painful. So can we use symmetries to constrain our architectures and make them more simulation efficient? And can we maybe use continuous fields to decrease the memory requirements and perhaps also to think about our data structures a bit differently? I'll also talk about whether we can actually learn how to represent feedback. So can we learn a continuous manifold where all these different simulations live? So similar to baryonification, but a la gradient descent. And finally, I'll talk about controllable simulators, so related to the problem of initial condition reconstruction and some stuff we've been doing in this area. But let's start with inductive biases. So recently, we had a benchmark of different symmetry-preserving architectures. So these are machine learning architectures that are designed to be, for instance, equivariant, meaning that if I rotate my point cloud, my output should rotate in exactly the same way. In particular, we had two tasks. So one is you have a point cloud of galaxies, and you're trying to predict the cosmological parameters. So this is the graph level task. And then we have the node level task, where you're trying to predict the velocity of those galaxies. So velocities should rotate accordingly, right? If you rotate your point cloud, whereas the cosmological parameters should be invariant to any rotation. And in particular, we looked at a set of equivariant architectures that are based on graph neural networks, and they use spherical harmonics. So in a graph neural network, you have this message passing framework where nodes, which are galaxies in our case, send messages to each other. And in this particular architectures, the messages are vectors themselves, or higher order tensors. So they're expressed in these spherical harmonic bases, and therefore you make sure your whole architecture can be either invariant or equivariant or whatever you want. But the architecture is very constrained by spherical harmonic representations. So now this bit of a debate in the machine learning world on whether we should actually do this, right? So this is what Rich Sutton called the bitter lesson, and is whether we should put any inductive biases in our architectures or we should use a scale in terms of data and compute. So basically, he's saying that what we've learned over the last 70 years is that general methods are the ones that end up taking over, right? Because they scale really, really well. So methods that continue to scale with increased computation, even as it becomes very, very great. And he says we want AI agents that can discover like we can, not which contain what we have discovered. So inductive biases go in the opposite direction, right? Making very specialized architectures that work under very specific circumstances. However, given that we have a limited computation, simulations are very expensive, and we do have exact symmetries, can we actually leverage them? So this is what we were looking at in this benchmark. And Simeon, if you want to pretend that you've done a lot of work, you put a big table. There, everyone knows. You've run loads of experiments. But don't worry, we're going to walk through it. So here we're going to be looking at the graph neural network. So this one doesn't know anything about symmetries. And we have, again, the graph task and the node task. So you're either trying to predict cosmological parameters or velocities of galaxies. So this is the performance of the graph neural network that doesn't know anything about symmetries. And this is what happens if we actually incorporate all those symmetries. Especially when you have a low number of simulations, it really outperforms it by quite a lot, right? So there's almost a factor of 2 improvement in sigma h, for instance. But also when predicting velocities, which is where we expected to have the biggest gain, is actually doing much, much better. Now, the winner, though, in predicting omega matter is the well-known 2-point correlation function. So I was complaining about one-dimensional summaries at the very beginning, but actually, they're not too bad. Now, but what's happening here is that the BOP has a lot of information on omega matter, obviously. And these graph neural networks are actually having a really hard time incorporating these long-range correlations. So what you can see is that if you combine the 2-point correlation function on only large scale, so just isolate the BOP and these equivariant architectures, then it's even much better, right? So it is finding additional information, but it's just not capturing those very long-range correlations. Now, for cosmology, we know the solution. Use the BOP, right? In other areas of science, we might not have something as controllable as a 2-point correlation function on large scales, right? So this means we need to really make more progress in architectures that can extract information across the whole range of scales. So this is more of a benchmark for graph architectures. For cosmology, I think we're fine with just using the large-scale 2-point correlation functions. Now, another interesting scaling to think about is what are we going to do if we want to analyze something like DESI with like graph neural networks or CNNs? Well, it just doesn't scale very well in terms of compute and memory, right? So if you think about a graph structure, because there is clustering in the universe, the number of edges just grows really, really fast, right? So for something like DESI, you'll have about 10 to the 6 nodes, the number of galaxies, and about 10 to the 8 edges. This is if you only assume you're connecting things very locally, right? So it's pretty bad. If you put on a mesh, obviously that's worse, right? Because most of the universe is empty. So OK, that's not a good solution. Well, can we do anything else, right? These both scale really badly to large volumes. How can we scale up? actually, you could think about representing continuous fields, right? So people in computer science have been doing this for other applications. But here I was wondering about two things, where we can use continuous fields as our data representation, but also whether we can use them to compress the outputs of simulations. So we've said that storage will be a big problem if we want to run this, like, I'm going to say millions of simulations. That's probably not going to happen, but a large number of simulations. So can we somehow store the simulation in the neural network weights? So what I mean by that is that you could input a position in the box and some time or redshift, and it will return the displacement field for a particle at that position at that time. So in a way, if someone wants a simulation, what you would do is you will give them the neural network weights, and they will reconstruct the displacement field themselves, and then they get the derivatives by just taking the time derivative, right? To get the velocity, sorry, by taking the time derivative. So that will allow you also to interpolate across time, right? So instead of having discrete snapshots, you could have this more continuous time interpolation. Now, this is still very early work, but you can see here the true displacement field in an n-body simulation. And on the right, this is the neural network estimated displacement field. They look very similar. There's still issues, right? So it's not a perfect compression. It's still lossy. But I think there is hope, because here you're overfitting to one simulation, right? So neural nets are pretty good at overfitting. This time we want them to overfit really badly. So I think it is possible that we will get to factors of compression, perhaps of a factor of 500. Now, what is the loss that we can take? That's something that's still to be seen, right? But the idea is that, OK, now you have these neural network weights that represent the continuous field at any time during your simulation. Can that be your data representation, just the neural network weights? Could you sample that? Like, could a diffusion model sample those weights? And is there something you can learn from a collection of simulations? Because right now I'm overfitting one of these continuous fields to one simulation, but time evolution is shared across them, right? So perhaps the subset of the network that could be shared, and then some other subsets will be overfitted to one simulation at a time to increase the compression factor as well. But this is all very speculative. We'll see. But I think there's a lot of promise on thinking about this continuous field ideas. Right. So the second problem I wanted to talk about is this learning the feedback manifold. So let me give you a bit more context about this. So we've been saying a lot of simulator 1, simulator 2 plots today, right? But if you had one simulator, like illustration G, another simulator like Astrid, same cosmological parameters, one game you can play is to try and embed them in similar places in a latent space, right? So you're basically trying to extract all the cosmological mutual information between the two simulations. And I think Yongseok might be talking about this after me, I'm not sure. But the approach I want to follow is complementary in the sense that I want a latent space that captures all the astrophysics. So instead of removing the astrophysical dependence, I want to capture the astrophysical dependence in this continuous space. So basically, I want a model that can produce baryonic fields, like gas temperature, gas pressure, etc., given the dark matter density field and this latent space. So I will call this like a generalization of baryonification models or bias models that will work with all the different fields and on very small scales. So Z, this latent space, that is, in this particular example, 5-dimensional, but it could be of any dimensionality, will capture all the properties of baryonic feedback. But all the simulations will live somewhere in this latent space. So it should be quite general. Now, this is related to ideas in representation learning. So this is a picture of the CMB and Jim Peels looking at it and seeing the power spectrum at the optimal summary statistic, right? We know that it's a Gaussian random field, so this is, if we want to extract cosmological parameters, this is what we should be doing. Now, we can also learn representations with machine learning, right? If we have a concrete goal, like generating baryonic fields. So how does this work? So you could either think about the generative approach, where you usually are trying to reconstruct observations. So in a variational autoencoder, for instance, you're trying to reconstruct an image. So you project it to a lower dimensional space, and then you try to reconstruct it. So the task is to reconstruct. Same with language, right? So you're trying to fill in a sentence like students at MIT are, and yeah, take your bet. Yeah, over-caffeinated. But it's the same thing, right? You're trying to fill in the data, so you're trying to generate it. You can also do the same with images, right? You generate missing pixels given a latent space. The other approach is the contrastive approach, where you're trying to embed closely matching pairs into the same point in the latent space. So here, for instance, you have two images of a dog, one that is like zooming in into a dog, and you want the model to know that this is still a dog, right? It's still the same object. So you embed them to the same point in latent space or close by, whereas a cat should be far away, right? So you have positive and negative pairs. Now, you have to make some assumptions on what your positive and negative pairs are, right? So you need to know beforehand. So that's why I'm using more the generative approach, where you can be more agnostic. You don't have to have specific pairings. OK, so how does this work? So you start from the dark matter density field. Now, you could train a generative model to go to any of the baryonic fields, right? So the example I'm showing here is using total matter, gas temperature, gas pressure, and gas metallicity. Now, you can also condition the generative model on a latent space. That latent space comes from the baryonic fields themselves, right? So it's taking the baryonic fields and compressing them to a 5-dimensional latent space. And then the generative model will extract the information that is relevant to solve the mapping between dark matter and baryonic fields in this 5-dimensional space. And this is actually how a projection of the 5-dimensional space in 2D looks like. So each point here is a simulation. And they each come from different simulation suites, right? So these are different astrophysical parameters within each simulation suite. So now you have this continuous manifold where they all live. But you can see that they live in different areas of the parameter space. So Simba always have a very specific place in the parameter space, whereas other simulations are more mixed up. Right? But the idea would be, can we now do more robust inference on this joined cosmology and latent space to constrain the astrophysical processes? So we can now interpolate between different simulations as well. Now, it's unclear whether the model is actually interpolating between them, right? We don't have examples of mixed feedback models, right? We might have in the future. That would be great. But yeah, the idea is that the model should be able to at least attempt at interpolating between different simulators. And I think we had some great talks during the week on how we're going to have awesome data across many different wavelengths to actually constrain this kind of latent space that can generate maps of any kind, right? It's definitely a very exciting time. But finally, let me talk about a third not super related project on initial condition reconstruction. Because I was saying that we don't want to do 5-dimensional cosmology, right? We would like to actually do high-dimensional inference for problems that are relevant. And initial condition reconstruction, we had Ben talk about today. So we would like to know what are the exact random phases of our universe. So we want to run it backwards and then show an example of using diffusion models to do this. We're wondering whether we could use a different kind of model that will actually maybe even learn the whole evolution backwards. Right, that's not what we're doing exactly now, but I'll show you the stage is at. But at least we wanted to be able to infer the initial conditions and the cosmological parameters and potentially get entire trajectories. That turned out to be very difficult, but at least we got to the initial condition reconstruction and cosmological parameters. So this work I've done with people based here in New York, so Adrian Bayer and Chirag Modi. Basically, we're solving this joint probability of initial conditions and cosmological parameters, split it into the conditionals, and I'll talk about the model that we use for reconstructing initial conditions, and then basically we have a normalizing flow for the cosmology part. Right, so how does the model work? So if you're familiar with continuous time normalizing flows, let me see if this plays. The basic idea is that you morph a probability distribution, the base distribution, x0, so starting with a Gaussian, into your target distribution. So this is your data distribution. By solving this ODE. So you have an ODE of how x should change between your base distribution and your target distribution, given by a learned velocity field. So this velocity field in the ODE is what your neural network is trying to learn. Now, this means that you can get your data by starting from the base distribution and solving this integral of your velocity field. So again, this is the base distribution and the data distribution. Now, in a diffusion model, the base distribution is Gaussian. But here, this is completely general, right? So the base distribution could be anything. In this case, we already have close matching pairs. We have the final conditions and the initial conditions. So x0 can be directly the final observation that we can take back in time. So the velocity field would be trying to take it back in time, basically. And this gives us a continuity equation for the probability of xt, because it has to be normalized as a function of time. Right? So we can also use the velocity field to compute probabilities. But it's not necessary, so we'll see. Because usually, your loss would be maximum likelihood. so maximize P of x. That means you need to solve the ODE. That training time, that's super expensive. And that's the reason why continuous time normalizing flows aren't perhaps as popular as you would think, even though they're super flexible, right? Because the velocity field could be any type of neural network. It doesn't have to be invertible. But still, the laws require solving an ODE, and that's super expensive at training time. So diffusion models, and maybe you've heard about flow matching, interpolants, et cetera, are all tricks to not have to solve this ODE at training time, so that you can actually make the problem tractable. Right, what's the trick we're using here? So, OK, we have this ODE, and we need to learn this velocity field. Now, can we regress the velocity field directly? Well, if we need the velocity field, there's no need for machine learning, right? We don't know the velocity field. But we can make some assumptions. So we can build what's called an interpolant between x0 and x1. So this is a function that interpolates between x0 and x1 in some particular way. And here, we're assuming there's a linear interpolation between the two. So now this defines the velocity field. We can add some stochasticity, and that's what allows us to sample posteriors, right? Because given some final observed field, we want to sample initial conditions that are compatible with it. So we need to have some stochasticity in this mapping. But the idea is that once you assume an interpolant, you have fixed the velocity field in expectation, right? So the expectation will be set by the derivative of the interpolant. And you can find all the derivation on this paper. But basically, we have turned the problem of maximum likelihood estimation that is super expensive to solve because of solving the ODE into a regression problem. So now a loss function is just going to be match the interpolant velocity field with your neural network. So very, very simple. At training time, you don't have to solve any ODEs. So super fast. So this is how it looks like in practice. So you have your final observation, and you're solving an ODE as a function of this fictional time. So S is not real time, it's not redshift. It'd be nice if it was, it's not. And you're solving this generative stochastic differential equation, right? Because you want to sample a posterior. So you're predicting a velocity field, but you're also adding some stochasticity to sample posterior. And this is how going back in time looks like in this fictional time. So you start from your observation, and you're going back to the initial conditions. But these intermediate steps are not necessarily matching any redshift evolution. We've tried some ideas, they didn't work very well. So if anyone wants to discuss this, that'd be great. But what we did is compare it to more traditional likelihood approaches with particle mesh simulations. So assuming a Gaussian likelihood and particle mesh, we can run Hamiltonian Monte Carlo. And we did it at 2 different resolutions because we want to check what is the convergence of these kind of methods as a function of the number of simulations. So on the y-axis here, you have the cross-correlation between the true and the predicted initial conditions for 2 resolutions. So one low resolution, so large box, a small number of cells, one higher resolution, so smaller scales. In both cases, we find that the model does actually converge to the true posterior, but it takes about 10 to the 4 simulations. So it's a pretty large number of simulations. But after that, obviously, it's amortized. But yeah, it's, as expected, expensive to train. We also compare the cosmological constraints from HMC to the ones we were getting. So basically, the purple contour is the model constraints, whereas the gray is the Hamiltonian Monte Carlo posterior. So it's very close, not quite exactly the same, but very, very close. And on on light blue, you can see what we'll get if we knew the initial conditions. That's not going to happen. But it's just, yeah, you can see the difference. And finally, something else we looked a bit into is whether we could actually generate initial conditions for more fuzzy constraints. So instead of having a final observation, what if I tell you, I want to simulate something that is a Milky Way-like galaxy. So that has the halo mass of the Milky Way and maybe a satellite moving at a certain speed, but I might not have a very exact density field I want to match, right? So people do this a lot by going to large volume cosmological simulations and finding an analog, right? Something that kind of matches your description, but it's hard to find something that exactly matches your description. So can we make it more controllable by conditioning this kind of models on a set of conditions? So far, we may work for something very simple, which is something like number of pixels above a certain density threshold. But ideally, we want to generalize this to more complex scenarios. And I think the timing wasn't too bad, 20 seconds left. But yeah, I'll leave you with a summary and happy to take any questions. Thank you.
Okay, questions? Yeah, over here, Jozef.
Thank you very much for impressive talk. I have a question actually about the second picture that you are showing here. So I guess you try to create this compressed representation of different feedbacks. Could you maybe comment on that? Have you tried some exercises, or what was the challenge there to interpolate between different feedbacks?
Right, well, the challenge is testing it, right? Because right now, okay, I can interpolate, but is this interpolation meaningful at all? We have no idea, right? Or even if you had simulations in between, right, that incorporate a separate model from one and mix with like AGN from one and supernovae from the other, right? Even then, it's unclear how to interpolate the latent space to match that kind of observation. So that is definitely challenging. And we still need to do this joint inference, right, to see whether this will actually work. Like, will it help with more robust cosmological constraints? And can we actually constrain this latent space with observations? So can we see where the real universe lies in this plot?
Yes, I agree that for a very detailed comparison, yes, but maybe one can still do something like compute the power spectra of such a generated universe to see whether it lies in between the two or something like that.
Right, yeah, you can do things like that, but the latent space is not necessarily linear, right? So interpolating it along the latent space could look very different to what you initially imagine.
Yeah,
but yeah,
exactly,
you can at least qualitatively say, okay, it's doing the right thing.
I was just wondering whether you did some first things or it's just so far.
Yeah, no, I haven't looked into that.
Okay, amazing, thank you.
Daniel?
Yeah, also here. So if you, just wondering if you have tried to use the TNG simulations, but over the 28 parameter space to see if in the latent space it looks like broader and maybe touching more of the regions that are sampled by some of the other models. I don't know.
No, that's a great point. Yeah, I should definitely add it here. Thanks.
First is, are you training simultaneously on all the 4 simulations?
That's right. Yeah.
Okay. So the second question is, so for the latent you mentioned like there is 5 dimensions. Did you ever try use any kind of special design laws to disentangle all those latents, or they're basically just mixed up right now?
Right. So something I skipped here is cosmology. So initially, okay, there's right. This here is also conditioned on cosmology, on the cosmological parameters, because, well, and at first I thought that would be enough, right? So if I condition on the cosmological parameters, Z will be free of cosmology, right? But that's not the case. So even though you condition on the cosmological parameters and you have like a strong information bottleneck, the model insists in keeping information about sigma 8. I guess it's hard to detangle it from feedback, right? So actually I have an extra adversarial loss that is trying to decouple Z from cosmology. The latent itself, no, the different components, yeah, they could be projected in any way. Yeah.
Any other questions? Yeah, Bucko.
So for the GNN, yeah, very surprising results. So you think that is really the architecture that is not able to get like the long range?
Right. Yeah.
So what about? I mean, have you tried to just put this into a regular grid and use CNNs or transformers or something like that?
Transformers also didn't work great at all. I think just because the data set is too small to learn like a good positional encoding. So if you did some pre-training, maybe you'd find something different. But yeah, transformers didn't help. We haven't tried the CNN on larger scales. Yeah, that might work.
But you use transformer on the data or on the graph?
On the point cloud. No, directly on the data. Yeah.
I see. Mm-hmm. And you were tokenizing and everything.
Yeah. And pretty badly, like, yeah, worse than the GNN. So yeah.
If there are no more questions, then let's thank Carolina again. Yongseok Jo is next.
Hi. Yeah. Hi. Today, I'm going to talk about robustness. So it's actually about robustness within the simulation models, cosmological simulation models, which actually it's about. What it's about is the similarity or differences within like subgrid models that are implemented within cosmological simulations, which we have seen like a lot today already. Several talks, we could see some differences from different simulation models like TNG, Simba, and Eagle, like that. So the problem of this is that when it comes to inference, so this is results from my previous paper, which is about calibrating cosmological simulation against observation. So what we did is we calibrate TNG simulation within CAMELS suite against stellar mass function and star formation rate history. But we got some results. Like we can see that we can actually calibrate the simulation. They can reproduce the observation. But the parameter that we get from that calibration can actually, that depends on the simulation models. Like so, for example, here we calibrated the parameters against TNG, and we apply that to Simba. Then we're going to have different results. Vice versa, we're going to have different parameters, even with the same observation. And also, we can see that it's Bucko's paper. So we train, I think it's gas temperature map. We train the machine to predict cosmological parameter using TNG and self-validation, and we apply that. We test this the machine to Simba. Then we're gonna have very different results, like here on the left, on the right, on your side. So here, what I like to do is find the kind of robust machine that can predict cosmological parameters in a way that it is not sensitive to the choice of cosmological simulation model. So the assumption here is that, let's say that we have like several different models here. Then there could be overlap and intersection and stuff. Then this intersection here, that can have like all three models could represent the universe. Like so, since universe has to be physical and our simulation has to be physical, that means this point should be very robust, has some robust physics in it. So that might represent the real universe. That was our assumption. So to do so, we have to get rid of, so let's say, so this is about robust estimation. So for this, like we're gonna suppress the classifiable information, leaving the common information within the simulation. So it's very obvious that the information within simulation can be divided into common across different simulations and classifiable across different simulations. That what we're trying to do is to suppress the classifiable information here. So to do so, we have this neural network structure. So there's CNN, encoder, classifier, and regressor there. So basically, what CNN does is just process the map that we're going to use, and encoder like compress the map into some summary statistics, which we call I'm going to call it latent variables. And classifier here is working as a kind of adversarial way, so that suppress the classification using classifier. And regressor, it's for just estimation, prediction for cosmological parameters. We have the big three loss function there. So the J there for just the mean square error, basically. So it's about the prediction, the error of the prediction. And H, that's cross entropy, and I is for mutual information between the latent variables and simulation data, so that we're going to have more, we're going to retain more mutual information, yet using the classifier here, make it declassifiable, then make the latent variables declassifiable. That's our goal. And we've used, for input, we used 2D H1 maps, density maps, and classifier here is going to classify like TNG, Simba, Astrid, and Eagle. But here we trained the model, our machine, on TNG and Simba and tested on the Astrid and Eagle. And the target cosmological parameters are omega m and sigma 8. So I'm going to talk about a little bit about latent space. So latent space basically is a collection of summary statistics, so which are from the input data. And the dimensionality of latent space is kind of high usually. We chose here like around 1,000. So it's for like analysis or visualization. It's really hard to like deal with a very high dimension. So we used a dimensionality reduction tool, which is called UMAP here. So we compressed it, like reduced it down to 3. So 3 here is actually kind of random number. But if you think it a little bit over, then we can say that, okay, in the simulation, we have to have at least 2 axes for cosmological parameters that has to be there, right? And the another additional axis could represent a classifiable, a classification axis. That was the kind of goal here. So if I visualize the latent variable space from the machine that we train, so here this is from encoder. Then here this axis 0, 1, since it's from like UMAP, so I didn't do anything. Like on my side, it's just a machine, kind of principal component analysis. So these 3 axes are here is very arbitrary, and but yet we can see some correlation between latent variable, or one of the 2 of these axes with cosmological parameters like omega m and sigma 8 there. It's color-coded with omega m and sigma 8. So here, up here on the top, we trained the machine without any robustness. So we didn't do any declassification. So they should be classifiable, the latent variables. But here, we impose some the classification power so that we can have like robust features, robust latent variables. And here, we can see some separation between 2 different simulations up there, like blue and red. Blue for TNG and red for Simba. But with robustness, we can definitely see that they're like blended. We cannot classify the simulation models using based on this latent variables. Then I'm going to show you some video for this the 3D reconstruction of latent space. Then we're going to see that there's 2 sheets of latent space from TNG and Simba are very close, but they're clearly separable. And then color-coded with omega m, sigma 8 and omega m. But with robustness, it's completely kind of blended and mixed together. But still, they retain the information about the cosmological parameters. So this is a zoom-in view. So I divided this data based on their omega m, the values of omega m. So lower omega m, mid, and higher omega m. Then we can see more clear distinction between TNG and Simba. Yet with robustness, they're like very mixed, and it's not actually classifiable. Then the next step is that we have to test whether this machine actually works on the precision, whether this performs very well on the predicting the cosmological parameters, regardless of the type of simulation model. So we tested on the Astrid and Eagle here. So this is before just random prediction. Then we're going to see what's going to happen with robustness. Oh, sorry. So this is for omega m. So it's a little bit busy. So here, down here with robustness, up here without robustness should be classifiable. And there are 4 metrics, which is about relative error, chi-square, bias, and alpha stands for bias over standard deviation, to be precise. Then this is self-validation. So this is training data, the tested on training data. That's for the machine tested on unseen data, which is Astrid and Eagle. Then here, with robustness, since we kind of force the machine to forget their classifiable information, it's kind of obvious that we have to lose some information. That leads to kind of degradation of accuracy here. So if you look at the relative error there, then we're going to lose some accuracy, precision there. But here, we're going to have better results, better prediction in terms of unseen data. So there, for Astrid, like 14.1%, now 11.1. It's not a huge improvement yet, but we saw some improvements. But with sigma 8, we can see more drastic changes with this. So here, again, the same here, the training data, that's unseen data. Then training data, of course, we're gonna see the degradation. But there, we can see there quite a lot of improvements, even visually, and even as well as in numbers. So all the numbers got better with robustness, so which is really great. And another thing is that we're going to see the very similar pattern across different simulations, right, with the robustness compared to the without robustness. But then again, we're going to look at the latent variable space and see how is this possible. Then I overlay these the third and fourth simulation, which is Astrid and Eagle on top of TNG and Simba. This is green here. That's for Astrid. Then here, without robustness, they're so biased. They're clustered at the edge of the TNG and Simba plane. But with robustness, we can see that it's spread it across this latent variable space. And also, if you look at the colors here, omega m and sigma 8, it's more now it's more Astrid is more consistent with the TNG and Astrid, right? Here and there. But there's some peculiar behavior in axis 2, which is for classification. That's we don't know yet what's actually happening there. But yeah, in terms of omega m and sigma 8, we can clearly see that with robustness, we can all 3 simulations are very similar now. That similar thing has happened in Eagle as well. Eagle here is coded with purple here in purple, and here it's biased a lot without robustness. But with robustness, we can see that all the purple dots are on top of TNG and Simba. So, and we looked at the latent space, and we calculate some numbers for classifiability. So this AUC score, when it's 1, that means it's completely classifiable, and when it's 0.5, then it's not non-classifiable. So here, there's some numbers for the combination of all four simulations. Then we can draw that diagram. So Simba is kind of outlier, so which we have witnessed already in different talks. If you look at the neutral hydrogen density map, it's very obvious. This is from 1P set. Then the evolution of the structure is very different in Simba. So we're going to think about then about this training, the achieving robustness within the machine learning framework. So there's different simulations, like TNGen, SGen, and Simba like that. But we don't really know how they are configured in the latent variable space, in any space that we can think of, right? It could be like this, for example. Could be very general, I think. Then when we train this machine using like TNG and Simba, let's say that's what we did, then what we can do is we can constrain this way, this plane, so that we can have, the best we can have is this intersection. But we can't really constrain this machine across this direction, which can include S-street in a way. So it could be we're going to end up being here, like after training with robustness, here or there. So there are a lot of like randomness in this training. So if we like end up being there, then we're going to have very high precision machine. But when it comes to here, then we're going to see a very poor performing machine. So this is kind of challenge. So, or theoretically, it's very impossible to get the ideal machine that can perform on the different simulations. Yeah, this is kind of a challenge that we have. So, but another thing we can think of is that, with this framework and about the robustness, is that not just predicting parameters in a robust way, but actually how the simulation has to be run in the future cosmological, very large size cosmological simulations. Then the first question or discussion that we have to have is that we're going to have like very diverse different models that we can cover all the space, all possible cosmological space or astrophysical space. Or we have to have this one. Here, I'm not saying that, but we all not saying that Simba is wrong, right? Then, but still, he's a kind of outlier. So then, what we should do? What should we do, right? That kind of question we have to ask ourselves, I guess. And another thing is that we can interpret. We have to focus on interpretation of these robust features, what they mean actually. And another, I think, funny project we can have is that we can, using that robust latent variables, we can think of that as like new statistics, right? Then if we can have that statistics, then which is robust against different simulations, then we can, like a power spectrum, but robust version. Then we can use that as another measure for calibration or estimation. Okay, thank you.
We have time for a couple of questions, maybe one or two. Oh, sorry, go ahead.
So this is great. I've got a list of questions. One is technical. So in your loss formalism, you have this contrastive setup. So I see you had a DK KL divergence term, which I assume was using to estimate the mutual information. The mutual information is like notoriously difficult to do, right?
Yeah, right.
Explicitly. So what is the actual operator that you're using for to estimate this?
So this is variational bottleneck.
Okay.
Yeah. So it's elbow stuff.
Okay.
Yeah.
What is the how do you calculate loss functions? Is it a density estimator type of thing? Are you lower bounding?
No, it wasn't about density estimator. It was based on the I kind of forgot what I did at the time. Yeah, I'm gonna talk about this like after this.
Oh yeah,
I kind of forgot. Yeah. About that.
And my more like bigger picture question is: do you think that so robust summaries are really useful, but do you think that you could link? Like, I think it would be ideally we'd understand like why if it's a feedback parameter in Astro that's throwing us off. Like if let's say you do both model comparison and you do your robust inference with these statistics on data, and we have in the hopefully not too distant future, the data says that okay, the three models that agree with each other also agree with the data, and Simba is weird. It's still weird, right? Let's say you have a couple of things pointing to Simba being weird. Do you think that there's a way in this formalism to understand why Simba's not as good, right? You might have a soup. You might have a soup of those three that agree with each other, and you've got that and agree with the data. But it'd be nice to know why the Simba's strange.
Yeah, that's kind of hard question to answer. But at the same time, I'd like to point out that even the Simba is outlier, and let's say that the other three are consistent with the data. That doesn't mean that that doesn't have to be the case where three simulations are really accurate or right. Right? We have to look at the parameters, and we have to look at the different physical aspects of the simulations. So these are from just the H1 map, and the prediction. Let's say that I'm going to predict all three or six parameters that we let in the CAMELS, but the result, the prediction, the estimation of astrophysical parameters doesn't make sense. That's possible, even though it's consistent with the data. It matches the data. So it's really I think we have to be really careful about those. But looking at comparing different simulation in terms of astrophysical axes is, I think, really hard. But I know that Chai and some students are working on trying to come up with the kind of bridging models between different simulations, like Simba and TNG. So that could give us some kind of notion or additional information about the different simulations. About the first question, it came to me just now. It was just some equation from one of the papers, which is about the variational information bottleneck. So there was kind of analytic equations. So based on that equation, we can talk about that later. So.
Yeah, I think it would be best probably to take that later. But yeah, thank you again, Yongseok Jo, and
thank you.
Next, we will hear from Kai Lehman.
You hear me, right? But there they are. Okay. Great. Good. 8 minutes. Good. Yeah. Hello. I'm Kai. I'm a student in Munich, and I'm gonna tell you about this paper here that we wrote on also actually learning summaries from cosmological simulations and then trying to understand something about these baryon models from them. Yeah. So I hope that this will nicely tie in with these two talks that came before me. Yeah. Okay, so I think this here I can keep very brief, right? So by now we all know that when we look at these hydrodynamic simulations, they have these very complex baryon models, and unfortunately they disagree in certain regimes. Yeah? And the cosmologists in us, they look at the power spectra of these simulations and they see, oh, the power spectra disagree, that's bad, right? And so a part of us, at least, are very interested in still doing cosmological inference on these scales. Yeah? And so the question is, how do we do this, given that we have these uncertainties? And at the same time, when we do this, should we even be looking at the power spectrum in the first place? Yeah? Because it's not clear at these scales that it's a very efficient thing to do to climb up this ladder of endpoint functions. Yeah? And so our idea here was, again, that we learn summary statistics about these simulations, and then ask, okay, given these learned summary statistics, can we actually understand something about these very complicated feedback models that enter these simulations? Good. So we choose to do this on the galaxy level, and there are these very interesting papers by, among others, that I'm citing up here, that have developed this framework of doing inference with galaxy graphs. And so you can see that it's a very natural thing to think about galaxy catalogs in this graph architecture. So I can just say, every galaxy in my catalog is a node in my graph, right? And I connect galaxies that are close to each other. And we also heard about inductive biases. So I can do this in such a way that I respect some symmetries that I think should be there. And so here we do this with translational and rotational symmetries. Okay, and to connect to these papers that have done this before us, we follow this approach entirely, and so we put in positional information about these galaxies and also velocity information. Good, so this is the entire framework that we have in the end, right? So we have these galaxy graphs, we put them into a GNN. The GNN gives us a summary, and the summary is passed directly to some SBI machine. And after the fact, after we have trained this entire thing, we ask, okay, can we understand what is happening here? Good, so just to show you very briefly the performance, so we are able to recover cosmological parameters, right? So these are marginal posteriors on omega m, and these work very well. Having said that, omega m works, sigma 8 is a catastrophe. So we can't say anything about sigma 8, but we continue here nevertheless. We think that this just comes from the fact that the boxes are so small, right? So we train this on the small CAMELS boxes. Okay, but after we have trained this now we can start thinking about what is actually happening in the summary statistic. So when we trained this thing, the length of the summary vector was actually a hyperparameter. And it turns out that this machinery works really well when the summary vector has lengths of about 60 or so, 60 to 80. Now, obviously, it's very difficult for me to plot anything in 60 dimensions. And so we follow the talks before me, and we try to, again, compress this down to fewer dimensions. And so we do kind of the two simplest things we could think of. On one hand, we look at the principal components, and we correlate them with things that we understand, with parameters and the power spectrum. And we look at the distribution of these summaries in isomaps, which is a nonlinear way of compressing the data. Good. So this first thing that we do is we can calculate these correlation coefficients, and we find, of course, correlations with the cosmological parameter. We also often find correlations with the supernova parameter. We never find the AGN parameters. And we can do the same thing here with the power spectrum. And so what I think is pretty interesting here is we can of course mix and match these plots, right? So I can see, the first principal component has something to say about something that is associated to supernova feedback. And I can see that this is roughly stuff that might be happening on these scales here. Good. One thing that is very important about all of this is that these summaries are actually very robust with respect to architecture. So we train 100 models or so, and here I show you the correlation coefficients of the best 30, and you can see a pattern definitely, right? So we always find these correlations, and we never find these AGN correlations, by the way. So these are always very, very similar. Good. Now we switch to a nonlinear way of representing this data, and we show isomaps of these simulations. So here in the scatter plot now, every point is one simulation, and we color them by the underlying baryon model. And you can see that apparently these green points here occupy a larger volume than the others. What does this mean? So the cosmological priors over these simulations are the same. So that means the difference here has to have something to do with these baryon models that enter there. And this also very nicely ties in with these papers by Nathalie DeSanti, where she has found, okay, I can train on the green points, and I can nicely generalize to the other points, but not the other way around. And we very nicely recover this in this summary space setting. Good, and these are very powerful statements if you think about it, right? So this is not me plotting some power spectra, right? But asymptotically, I get the entire information that I put into the simulation in the first place, and into the model in the first place. Good, so we can also color them according to input parameters, and we find that in this isomap representation here, okay, omega m lives on this radial, on this polar angle, and the feedback parameters, the supernova parameters, live on this radial angle. But now we ask, okay, can we actually quantify this a bit more? So can we find a region in the summary space that I, as a human, can understand? And so we had a strategy for this, which is we emulate. So we train an emulator on an L2 loss to predict the summary statistic given only the cosmological parameters. And what we expect to happen here is that the emulator will average over all of the parameters it doesn't know about. And so this is exactly what is actually happening. So here you can see in black the same summaries as before, and colored are now the summaries that I have emulated. And you can see that I actually pick out this direction that I have kind of loosely identified by I here. I pick out this direction here very precisely. And this actually is happening in the high-dimensional space. Right? So I'm training this emulator in the 60-dimensional space that I cannot plot. And so this is completely independent of the way I choose to plot this data afterwards with these isomaps. And so this is to show that we can actually start finding something like coordinates that describe this manifold where these summary statistics live on. And this is kind of the direction that we wanted to push this into further, right? Can we find more numbers that actually characterize these dynamics that come from these CAMELS simulations? And I think I'm out of time, so I'm just going to show this last slide, and thank you very much.
All right, questions? Oh, sorry, Bucko, come on. Yeah, go on.
Very nice. I mean, I know I'm very familiar with this. So basically, you have the latent space and you do a PCA. So have you tried to do like UMAP or Disney?
Yes. So we do PCA in this first step, right? So when we do these correlation games, this is PCA. This is already no longer PCA. This is isomaps, which is nonlinear. But you see the same thing. If I were to just plot PCA components, this volume argument you would still see. So this is also, we choose many different ways of pushing this down to 2 dimensions, and we also always see this. Reason why I don't show PCAs here is because I'm afraid of projection effects or so, right? And isomaps, I think, are pretty robust to this.
Yeah, sorry, go ahead.
So you varied, also, nice talk. You varied the number 60 as the number of numbers you need to describe what's changing in your data. So that's to get from massive data space down to 60 numbers, which is already a massive compression. This might be sort of a silly question, but did you try compressing those 60 numbers down to 2 numbers? So using the same loss you did, and if you did you lose information there?
Okay, so I didn't try to do this after the fact, right? But I mean, so I can still treat this in 60 dimensions pretty well with like this emulator method. But I'm sure that if you were to force it, right, you should be able to find lower dimensional representations of this data as well. I agree with this. So what we do, by the way, so the hyperparameter search we do is from 2 to 200. Yeah, but I'm sure if you really wanted to force it, you could compress it down to fewer numbers.
Okay, any other questions? If not, then let's thank Kai and let's go. Next is Jozef Bucko.
Yes, thank you very much. Can you hear me? Yeah. I'm Jozef Bucko. I'm a postdoc at the Institute for Particle Physics and Astrophysics at ETH Zurich, and I would like to talk about a project that closely relates to what Arne Thomsen was describing yesterday, which is we try to do simulation-based inference for galaxy clustering and V-cleansing in the DES year 3-like setup, and actually this is a DES project, so I'm doing this with Arne, with a couple of group members, and also within the DES collaboration. And I think I don't need to spend a lot of time with motivating that it's very beneficial to look into the non-Gaussian part of the large-scale structure. There are many works to describe that, and particularly the one led by our former colleague Dominic Zurcher, that he was doing very similar thing with V-cleansing only and with with convergence peaks extracted from the DES year 3 like footprint, simulated footprint. And what he found is that one can, of course, gain a lot of information on cosmological parameters by going from traditional CL analysis to peaks, and then essentially also combining those two to reach maybe factor of 2 or something like that, improvement in constraining power. And of course, one can try to play this game of using different kind of non-Gaussian statistics, peaks, scattering transform, Minkowski functionals, and others. And there have been papers, for example, Ayani et al. And others that try to compare which one is better in a specific setup. But what we are focusing now in this work is galaxy clustering peaks and convergent peaks. And these are often very challenging to model theoretically, but are rather easy to extract from simulations. And of course, for that one needs such a simulation, and what we are using, simulation suite actually, and what we are using is CosmoGrid simulation suite that was published roughly 2 years ago by Kapchak and others. And what he showed on the top of the CosmoGrid simulation itself, that when one would combine different probes, like weak lensing and galaxy clustering in this case, one can gain a lot of information. And I don't need to talk about benefits of probe combination here, I suppose, but looking, for example, on the two contours, which are the traditional CL or power spectral analysis, already there one can see quite a bit difference, and that has been reported by many other works working with both simulations and real data. Now, this then defines the project that I'm working on, which is combining weak lensing and galaxy clustering on the map level with SBI and using peak statistics as a probe of non-Gaussian field. And this is, as I said, the DES project. Now, let me spend a couple of moments on mentioning the CosmoGrid simulation suite, which was run at in Switzerland, which it comprises more than 17,000 independent n-body runs in something we call grid. So then we have a lot of cosmological parameters and multiple realization per cosmology, so one can try to inspect cosmic variance. Then we have something that was already mentioned in context of Quixote, that we have fiducial, where we have many realizations, so one can try to estimate, for example, covariance matrix. And then we have benchmark suite of simulations that is much smaller and has higher resolution, so one can test models and approximations. And if you are interested, I invite you to visit cosmogrid.ai, where you can learn more details about the simulation, the data products, and everything else. Now, back to my project. And this will be also a scheme that has been in a similar fashion shown already. At the beginning, I have my simulation suite, CosmoGrid, and at the end, I would like to have my final posterior given the data that I would like to probe. And then we have the forward model that Arne was describing in more detail yesterday, so please refer to his talk if you want to learn more. And we get the simulated maps in the DES footprint, and these two maps are the weak lensing convergent map and the galaxy clustering number counts. And then we can extract our non-Gaussian statistics, which is peaks. And Arne was talking about machine learning-based summaries yesterday. So it's conceptually pretty similar with different flavor. And then with some additional compression layer, we train a neural likelihood based on normalizing flows. And then we inject a data vector that can be either from internal CosmoGrid simulations or some external DES-like mock, or the real data eventually, and then get the final constraints. Now let me show you a couple of things or knots that we can turn, and we need to figure out how to turn them before we can really finalize our contours and go to the real data. And one is, for example, how much smoothing we apply to our simulated maps. So here you see the contours provided for from the clustering maps only. And you'll see that if we smooth less and less, this goes from blue to green, then of course our contours shrink, and we need to figure out where to stop, not to throw away too much information, but still not to have biased results. And then additional thing that we can do is, for example, once we figure out that we can be conservative at a given level, then we can also employ something that is called multi-scale peak approach, where we say the peaks can also bear some information for larger smoothing, because it's not like power spectra that can be cut at different k, and then there is just superset of information if we go to smaller scale. So we can combine multi-scale peaks and can go from blue contours to orange contours essentially for free, because we can just throw in peaks with larger smoothing. And then, of course, the probe combination, that is the ultimate motivation of this work. And this is, again, the contours that I get from evaluating on the internal simulations. And you can see the green contours, which are obtained from galaxy clustering only maps. And then the red one, which are from the weak lensing. And then the combined ones, which are from both. And you see that, indeed, also in the setup with peaks, we have a lot of degeneracy breaking. And we see it in the left for the cosmology parameters, and then also for the nuisance parameters, so intrinsic alignment, amplitude, and the linear galaxy bias. And we see that adding the additional probe can actually help constraining those parameters, and in return also cosmology. And now let me conclude with this slide about validation procedure. And it's a crucial step to figure out how conservative or aggressive can be with the smoothing. And for that, we do tests that were performed in similar manner in McCran et al. For DES year 1, where we have external simulations and the DES like galaxy catalogs with the same color cuts and everything. And one evaluates our model on these external simulations and see at which level we start to be biased. And of course, the ideal scenario is that we have multiple realizations of each of them. We have diverse galaxy catalogs, and then we hope that the real data fall somewhere in between those. And if we are robust in multiple different catalogs, then we also are ready to go to the real data. And now, but in reality, we have only one buzzard flock that has multiple realizations with the DES-like MOCs. And you can see here what happens with our contours if we smooth more and more. So what I'm showing here are the peak contours when I evaluate them on the individual, on one single buzzard MOC observation or MOC catalog. And then if I do the combined posterior, which is the red one, and we see here I'm just too conservative and I'm going too much to small scales and my model is not good enough. And I'm very biased compared to the underlying cosmology, which is lying at the intersection of the two dashed lines. And then, of course, I need to smooth more, getting closer. And then if I smooth what I would call enough, then I can recover the underlying truth of the simulation. And then we can play a similar game, so add contours from different simulations to see if they scatter reasonably well compared to, for example, what we recover from buzzard. And with this, I think I would conclude and just shout out that there are different work with Cosmogrid combined probes that we are trying to do. I was very excited to hear about Carolina, because this is very similar to what we are trying to do with this DES plus disk proposal for generative AI and LSS. So please, if anyone is interested or has some ideas, I'll be happy to chat. Thank you.
Thank you. Okay, questions?
Everyone wants the coffee.
Oh, okay. There is one question over there.
Yeah. So when in the last contour plot that you showed, when you're adjusting the smoothing length, if I understand correctly from your simulation, so if you're working with real data, or even in a simulation suite where you don't, or even in a comparative simulation where you don't know the underlying cosmology, are there any other things you can look at there to determine like what the right choice of smoothing length is in those scenarios where you don't know the underlying truth?
Yeah, it's quite difficult. So maybe there are some ideas, but our approach is really to take a very diverse set of scenarios where we know the underlying truth and make sure that for different galaxy catalogs with different galaxy population approaches, we can still recover the truth. And yeah, maybe we can chat about some ideas what to do if we don't know that.
but in our work we just rely on the kind of test that I mentioned.
Okay, cool. All right. Well, let's thank Jozef again.